Hi, welcome back to CET3116 Digital Technology. In this video, we want to review counters, but from a different perspective. We want to start looking into counters design. Actually, it should be more than counters design because this is the first step to understand how the sequential circuits in general is designed. So we want to be looking into a general approach that allows us to understand how the design of any finite state machine can be done in general. All right, so starting with binary counters, if you know exactly what the sequence is they want to apply for the counter, and you want to start the design, well, the first thing you need to do is to create a graph, and that's what is called a state graph. And pretty much it will give you the sequence of different counts that we have. So remember, if we have a counter that counts from 0 to 7 or modulo 8 counter, so we'll have 3 bits, and we start counting from 0, 0, 0, 0, then 0, 0, 1, then 0, 1, 0, and so on until we go back to 0, 0, 0. So if you see this, we can create a graph that pretty much depicts this behavior of the counter. So once we have the state graph, then we create a state table. And that state table is pretty much what we have in the state graph. You have the present state, and then for each one of the changes of the clock, in this case, you will have a next state, and that's going to be also depicted or clearly put in the table. Right? Now, once we know the number of bits for that particular counter, or better yet, the number of states if we're generating a generic finite state machine, then we know that we will need one flip-flop per bit. So for instance, if we have a graph that has 8 different states, you know that it will be enough to handle that finite machine with 3 flip-flops. If you have, for instance, a counter that goes from 0 to 3, then we know that it would be enough with 2 flip-flops because we have only 2 bits. Okay, only 2 bits are required to count from 0 to 3. If we have one that goes from 0 to 31, then we will need 5 flip-flop because we will need 5 bits. So in other words, there's a strict correspondence between the flip-flops and the number of bits. Now, the other thing that we do is using kernel map, and then with the state table, we simply using the flip-flop for obtaining the input to each one of the flip-flop. And the flip-flop we want to see could be either T flip-flop. We want to start with T flip-flop, which are the toggle flip-flop, are really easy to work with them, very straightforward. Then we're going to start looking into D flip-flop and SR flip-flop and JK flip-flop. Very briefly, all right? Okay, so here's the first example. We have a 3 bits up counter, so we're supposed to count from 0 to 7 and then repeat the sequence again. So our state diagram will start with the first count, which is 0, 0, 0. Then when the clock comes, what's going to happen? The clock comes and then we're going to increment the count. So in other words, we change the state. Our state here is 0, 0, 0 and go to state 0, 0, 1. Again, it is a counter. The counter is straightforward. It won't change. But if you start thinking in terms of all possibilities of a finite state machine, we may have different next states given by different inputs, etc. So, but let's not go to there now, and let's keep doing this exercise with the counter. So once we reach the first count of 0, 0, 1, what's going to happen? Well, the clock will come, and then we go to the next count state, which is 0, 1, 0. So here's 0, 1, 2, and then 3, 4, then 5, 6, 7, and then back to 0. So this is our state diagram. This is a finite state machine because the number of states is limited. All right? Good. Now, here's a very important thing that we're going to get from this class is the way we approach for any design in sequential circuits. So we can list all the present state or all these states, right? Those are the state from the counters. We start with 0, then 1, 2, and so on and so forth. At some point, we may think if we're here, this is our present state. Suppose that at this moment, the clock has not come yet, and then we start just counting. We count with the pace of the clock. The clock change, we increment, we change the state. Now, that's what we call the present state. But the idea of calling this present state is to contrast or to put in evidence what is going to be the next state. So the next state, for instance, will be the next cycle. In this case, what the next state for 0, 0, 0 is basically what is following in the count. This will be 0, 0, 1. So this is our next state table, right? And then what we need to see is that's pretty much the secret. Each one of these next state or each one of the bits of the states, remember, will be controlled by a flip-flop, right? So a flip-flop will be pretty much the major player in letting these changes to occur and then go from a specific state to the next state, okay, from this count to this one, or incrementing the count. So in order to design that, we can say, okay, let's see if we start using toggle flip-flop. We have seen some examples in past lectures in which we use, for instance, JK flip-flop. I will be pretty much the same idea because the way we use the JK flip-flop is exactly as using our T flip-flop or toggle flip-flops. Now, if we want to use then the T flip-flop, remember the truth table, I want to show you later that if we want to change or toggle, then T or the input to the toggle flip-flop should be 1. If we want to keep the state as before of that flip-flop, I mean no change, then T is 0, right? And then suppose that I look into each and every one of the flip-flop. Remember, C is going to be originated by one flip-flop, a T flip-flop in this case, B is going to be driven by another T flip-flop, and A the same thing. Just remember, when we have this, A is going to change 0, 1, 0, 1, 0, 1. So if you look only this column belonging to A, and you require to do that changes using a T flip-flop, what input would you use? Well, you would use T in such way that is always 1 because I always want A to change, right? How about B? Well, if you look into here, B is gonna change from, in this case, when we have A equals to 1, right? Every time A is 1, the present state, next state will determine whether B is going to change or not. So A1 here, then you see that the B changed from 0 to 1, right? In this case, we may use simply a T flip-flop that changes whenever A is 1. Okay, A1, B changes. Here, A is 0, B is the same. Okay, here, A0, B is the same. And what about C? Well, C will change in this case, as we have seen in some examples with the other counters, that in this case, C changes whenever A and B both are 1. So at this point, if A and B, in this case, we have 1, then we have a change. And we have seen that before, right? All right, so how do we then use the T flip-flop for that? Well, I already mentioned that for the case of A, let's see all the 3 T flip-flop. That's going to be the behavior of the T flip-flop. So for the case of A, remember A in this case is the least significant of the bits, and it changes every row. So 0, 1, 0, 1, 0, 1. Now that demands my toggle input should be always 1. Change from 0 to 1, from 0 to 1, back to, and so on and so forth. Okay. B is going to change when A is 1, right? And and that will correspond to this present state, A1. Okay, no, doesn't change here, but change here. It changes here again, and it changes here again. And regarding C, C is going to change only when A and B both are 1. In this case, and also in this case. Now, from there, you see, we already have the state diagrams, which is this, all the sequence. We, using this state diagram, we design our table. We simply bring the table, okay, and with the table we start our T flip-flops. In this case, remember, we're designing with a specific type of flip-flop, which is a T flip-flop. Now, let's see how the design is in circuits fashion, and this is one supposition is that all flip-flop will change state briefly after the rising edge of the clock. So we can choose a falling edge or whatever, but we're going to see that every one of the flip-flop will change at the same time, okay, with the input of the clock. And here's the circuit. Okay, this is the circuit that we just designed. So it is the counter that we already seen, but we step by step follow a procedure that brought us into this design. Okay, the way we can prove that this works is, well, we can do a waveform. Remember, this is our clock. In this case, we're using rising edge flip-flop. You could use falling edge, that doesn't matter. The change of the clock will be determined in different ways. So this is the clock, and then remember, A is going to change, right? Because it's a toggle. When we have every clock change will have a change on A. Okay. So this clock we go from 0 to 1. This clock will go from 1 to 0. This clock 0 to 1. This clock 1 to 0, and so on and so forth. Now, remember, in this circuit, we feed TB directly from A. So what's going to happen? This is going to be TB, which is exactly A. It's the same wire. And now what happened? Well, in this case, how is that change gonna, that B is going to change? Well, at this point, remember, when you read this, the rising edge of the clock here will check the input, and the input actually is 0. So it's not changing here. Whenever this clock comes and check the input's going to be 1. So at this point, we will have a change in B. All right? And the same thing, right? And at this point is when TA is 1 and then a new change comes in. Okay, so the way we read the events is with the rising edge. So read here, the rising edge, read the situation briefly before, and the same thing here. All right, so now the third or most significant of the flip-flop, which is C, the input of the flip-flop is AND of B and A. Okay, so if this is what we have, then we only have a 1, for instance here, right? Let me see, let me show you. In this situation, we have A, right, and B. Both are at 1. Therefore, only when these two are 1, here and here, then we're going to have this TC equals, let me, the other way around, sorry. That will be TC, okay? So C is 1 when A and B both are 1. At this point, right here, right at this clock, that is pretty much this one, is when we're going to see C changing, right? So this is the sequence we already know from our examples of the 3-bit counter, synchronous counter, but now designed with T flip-flops. Now, here's how we are supposed to be able to draw the equations for any type of sequential circuits. So if you have the state diagram, if you have the state tables, see that we could derive the changes from the present state for each one of the bits to the next state, how this bit changes. Okay, we can produce that in a table for each one of the flip-flops. Better yet, we could use kernel maps. Okay, we then, for A, well, it's no problem because A is always 1, right? A is always 1. Let me use the arrow back. Okay, we from the same example, we know that A is always total for A is always 1. But B and C, well, that's a different story. So this is the total of the B. Now, how do we figure this out? Well, in this case, if you look into the table, see, imagine that the present state is given by this simply the values of C, B, and A. Those are here the present state. If we put that in a table, that would be the table for present state. Okay, so remember the output or the T value will depend not only in that particular bit, but may depend on the other bits. For instance, it's clear here that TC depends not on C, but depends on B and depends on A. All right. So they all are part of the factors that may possibly change. So see that how exactly is that B is going to change. So we know that B changes every time A is 1. So what's the region here in the K-map where A is 1? A is 1, remember, here and here. This is A equals 1. So at this point, I want then to change my my B. Therefore, the toggle should be 1. Okay? The next will be the same thing for C. When we discover that C should change, or the toggle for C should change whenever A and B both are 1. Remember that from the truth table? Okay, then here is the case in which B and A both are 1. At this point, I require a change on C. Therefore, my toggle C will be 1. The rest, no change for C. Okay, so TC is equals to B. Perfect. So we have one step now guaranteed that we can develop using K-maps, and it's something that is not guessing as we sort of did before, but just a procedure that step by step take us into the design. All right. Now let's see another example, which is a redesign of the same counter, but using now D flip-flops. Well, the way we can think in terms of D flip-flop, if you remember, our D flip-flop can be built using T flip-flop, starting from that. If you remember, if this is our D flip-flop, we use a XOR gate here, and then we feed back the Q, and our truth table would be basically this one. Okay, remember, all we need to think is, okay, what happens if T is 0 and Q 0? Then because this is TX or Q, will have a 0. So 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, and 1 XOR 1 is 0. So you see, this is essentially our toggle flip-flop, right? Our D, which is Q next, will have exactly this T XOR Q. Now, these two first are not whole. The T0, and remember, when T0 in a toggle, the toggle doesn't occur, of course, when T is 1, right? Now, all we need to do is simply supplant this for each and every one of the, we take, this is our toggle flip-flop, and the inputs that we have before, we simply change. Instead of having a toggle flip-flop, we have a D flip-flop with an XOR. All right? And connected just following this approach. And this is exactly what using D flip-flop for. Now, if you want to check that, and suppose our procedure is to follow the state table and then think in terms of flip-flops, okay, we can deduct the equations for D. D A is exactly whatever A next is going to be. And for that purpose, then remember that we are interested in A naught, right? So in other words, we want to change all the time. All right. Now, that will be what we require us to put here to have a always tolling. Okay, 1 0, right? In this case, will toll, and they give the 1 or the 0 depending on what exactly what. And these are the other equations. But see how, let's try to find out in much more secure or a regular step, and that's using the kernel maps. Okay, for instance, this is the as I said, present state. In the case of C, okay, if you are looking into, well, this is my C is going to be 1. This is what counts as that. This is going to be 1 0 0. Or the next step of the next value that the C is going to have will be accounted. What comes after 1 0 0? It comes 1 0 1. As you can see, this count should be 1 0 1. So the 3 the three outputs of Q next are exactly the same as T, because this is the D flip-flop, sorry. Okay, so let's start from 0. This is our first count, 0, 0, 0, 0. What would be the next count, 0, 0, 1? C doesn't change, B doesn't change, but A changes. A goes from 0 to 1. We have 0, 0, 1 would be next. Let's see what is 0 in this point. 0, 1, 0. This is the sequence. What would be the next? The next will be 0, 1, 1, right? The next will be 0, 1, 1. And then here we have 0, 1, 1. Oops, let's see. 1, 0. Sorry. We have 0, 0, 1, and then we'll have 0, 1, 0, 0, 1, 0. My mistake. Here we have 0, 1, 0. We will have 0, 1, 1. 0, 1, 1. Then at this point, the next after 0, 1, 1 would be 1, 0, 0. 1, 0, 0. In other words, you can do the whole 8 counts from 0, 0, 0, 0 here up to 1, 1, 1, 1, and then you can find what should be the value of the Q next, in other words, the D. And this is revealed here in the flip-flop, okay, in the K-map for the flip-flop. Now, it is easy to figure out here, for instance, that this equation obeys what we have here in the K-map, right? This is A naught. This is clearly A naught here. In this case, this is B naught A or B A naught, which is what we have here, which is B XOR A. For the case of C, then we have, in this case, well, we have these two. This one is C B naught, okay, C B naught. This one and this one will be C A naught, which is this, and the last one here is itself is C naught B A. Okay. So, and these are the questions, but remember, it's not something that, you know, this is the mere casualty that we see in here. Okay, the mere coincidence that we analyze that. No, we have a procedure in which we simply put everything in the next state table or use the K-map so that directly give us the value of the for each one of the flip-flops, or how we drive the input to get the output that we require. Okay, I have another example, okay, that is a state graph of a up and down counter. Up, okay, I have 7 bit, 7 from 0 to 7. It's a modulo 8 counter that counts up and down depending on the sequence. Okay, so if we put a state table, that is going to be our state table. Okay, this is our present state, and this is the two different future next state. Okay, that goes from C plus B next and A next. So C next, B next, E next. Either if we are counting up or counting down. So it's like playing with two different tables. Okay, we strictly want to work with that. This is going to be the result. And it's pretty much doing the same thing that we already did using this D flip-flop with the XOR, right? And the only thing is that we need to include whether if we are counting up, then we need to select that using these AND gates, or if we're doing down counter. There's one restriction in which we cannot count, we cannot have suppose that we have, this is going to be a bit somehow as we depict here, we cannot have both of them at the same time in one. So it doesn't make any sense. It's not legal for up-down counter to have both up and down. Usually you have only one input that selects up or down. Okay, that's the most of the counters works in this way. All right. So see, we're gonna be looking at something that perhaps is not easy to grasp. That's the first time that we're gonna be working with 5 variables K-maps. So we have, in this case, what are our 5 variables? Well, we have our A, C, B, and A, but also we're using either up and down. This is 2 extra variables that makes 5 variables. And this is the way we do. So we have like a 4 variables map for D 0 or down equals 0, and another one for down equals 1. So in this case, we're trying to count up. Of course, at this point, we know, okay, that it's invalid to have U and D both in 1. So that's the restriction that we have. We, of course, can have both in 0, and when both D and U are both 0, that means that there's no change. We're not counting up, but we're not counting down either. And this is our K-map for that, right? Exactly, we can see depending on whether we're doing, for instance, in this case, if we're not counting up nor down, then everything is going to be the same. So in this case, this is for the variable A, the bit for A. And A is going to remain the same. So this is A, is going to be 0 here, 1, 1, and 0. Okay, the same thing for B and C, which are a couple more pages with that particular case of B and C. Now, this is what we bring as the next state for A. Okay, so suppose if we're counting up, and our initial sequence in this case is going to be, for instance, 0, 0, 0. In this case, we have sequence 0, 0, 0, or could be, for instance, this case 0, 0, 0. Actually, this one with the counter in up. Okay, that's 0C, 0B, 0A, and counting up here. Well, A is going to change, as we've seen before. Okay, whenever change also, what A is 1 here, at the same here is 0. Okay, again, and we're changing for this input U is 1. We're going to change that. This is exactly the same case, right? So we have this case in which A is going to be changing, or when A not. It's clear here, the same thing. And in this side, we'll have when we're counting down. Okay, this is counting down. If we have, for instance, our sequence is 0, 0, 0, then we simply wrap around backwards, and then we get from 0, 0, 0, we get from 1, 1, 1. And A will then turn to 1, either here, right, or whenever. If we have, for instance, 1, 0, 0, then counting down will be 0, 1, 1. So A requires to be 1, and so on. Okay, and the same thing here. Okay, so for each and every one of the state, this is the present state. This is the present state, and this is what I'm interested in. This is the K-map for A. Okay, this is how A should change depending on what the variables here are. This is the next state for A. Okay, one counting up, in this case, and the other counting down. All right, now we can see this, and this is what the book has. Okay, so remember, you read that if we have this common, for instance, the green, we can use the don't care. It's sort of imagine that we overlap these two K maps, one over the other, and then you can also find that this is adjacent. These four here are adjacent to these four because they're exactly on the same set of variables. Okay, the only difference is D. In this case, D changes 0, 1, and this is the variable that does not. Okay, but aside of that, there's nothing else common, and then we can use particular with D1 here. So the one that is common is the one in green that doesn't depend on D, and that would be A not U. So this is U, and this is A not. Okay, for the four rings. And then A not D, in this case, is here. This is A not D, is the red one. And finally, this one is A U not D not. Okay. And then, well, we simply group the terms, and this is what we get. That's what is depicted in the book. We can do exactly the same thing for B. Okay, this is the bit B, and this is how B changes. This is the next state for B. Remember, in this case, we're using also D flip-flops. Okay, that's exactly the same idea that we're using the same D flip-flop, but now we're counting up and down. Okay, so we can do exactly the same thing, and remember, at this point only we have these two common, so they don't depend on D. And our next state for the B would be this, right? We group, and then we pretty much arrive to the same formula from the book. Okay, and now the same thing for C. Okay, it's a bit more elaborated. We have more elements here, and it's more tricky. Actually, we have common for both maps are this in blue, okay, and this green, and this red. They're all both. They don't depend on D. Okay, so remember, we're overlapping these two maps, and this is adjacent with this blue, the green is adjacent with the green, and the red with the red. But this is not common. Oh, on this one, the violet also is part of it. So you can see that dependency on D is actually from these two elements, the one in orange. Okay. Okay, and that's basically what I wanted you to see as a method to designing counters, or in general, that would be pretty much the same approach that we do when designing sequential circuits. Okay. Okay, hope that everything got okay. I want to continue a bit more into the next session.